Okay, in this lecture, we're going to talk about the metric system, sort of the history and some basic abbreviations and definitions of the metric system. So let's get started and just sort of outline when the metric system was really developed. So in the English system, which a lot of us in the United States might be more familiar with, we use inches, pounds, gallons, this type of unit. But in the late 1700s, the French government actually was the first to sort of collectively get a bunch of scientists together and make some sort of universal system of measurement. So the government decided, let's get the 10 to 20 smartest scientists in a room, lock them up, don't let them out until they come up with some system of measurement. And the reason why this was important is because around that time, there was a lot of international trade. And it really depended on what port you went to, what the conversion factor was. So, the French were smart that you could really get a better exchange rate at certain ports if your unit of system was really dependent on locally how much something weighed or what the size of it was. So, for instance, a bushel of wheat might be different in port A versus port B. And the French realized that people could take advantage of this, so we want something that worldwide is going to be measured the same. Now, that was way back in 1790. In 1975, Gerald Ford, actually, president at the time, signed an official metric conversion act. However, although we sort of adopted it then, and we were the last nation in the world to adopt the metric system, we still don't really use it in daily life. So there would have to be some other impetus from Congress or a president to actually put it into action. So all that sort of history aside, here's some basic units of measurement in each of these types of systems. So length, in the United States, in the English system, we have feet and inches. In the metric system, it is the meter. In mass, you use the gram or kilogram. In the English unit, you might have ounces or pounds, right? In volume, usually in the metric system, that's liters, maybe milliliters. In the English system, that could be pints, cups, quarts, gallons, etc. Time is the only thing here that's universal, of course, and we all sort of use seconds, minutes, hours. So that's sort of some background of the dates of when these things were sort of developed and put into office as it was. But really, the metric system is what we're going to concentrate on today. A little bit about the English system, just because we have to be familiar with it, because it is still used in certain places. Scientists, though, regardless of where they live, use the metric system. So, this is a chemistry class. As a chemist, you are going to record your masses in grams or kilograms or milligrams or some, derivative of this base metric unit of mass. So the beautiful thing about the metric system is that there is a single base unit. That's really what these are here. This column, these metric units, those are the base units, and these are the base symbols. So for gram, for mass, the base unit is the gram, and the base symbol is the lowercase g. Okay, and be careful here, it's not an uppercase G, it is a lowercase g. Same for meter, it's a lowercase m. This actually is a typo. This should be a capital L. Just testing you. Hopefully you caught that. This should be a capital L. They're fixed. Second, lowercase s. So meter, second, and gram are all lowercase. The liter is an uppercase. Now, the beautiful thing is that with this base unit, you can manipulate this base unit with factors of 10. And factors of 10 are nice because, well, when you write these things out, it's just about adding another 0 to go from 10 to 100 to 1,000, or adding a 0 before the 1 in decimal points to go from 0.1 to 0.01 to 0.0001. Okay, and so it's just easy to convert things by moving decimal places than it is to multiply by something like 2.54. So this is the metric system. You have these base units, and then you add prefixes to these base units. So we're going to add things in front of these base units. And a gram we might change to a kg, where k is the prefix, or kilogram. And we'll go over all the ones that, as scientists, we really should be memorizing. This figure sort of puts in picture what I've said in the first two slides in words, how sort of innocuous the system is that we use here in the United States. So maybe this is a little hard to read on the screen, but this says 12 inches to a foot, 3 feet to a yard, 1,760 yards to a mile. So this is converting different units of length: inches, feet, yard, mile. 16 ounces to a pound. So all these numbers are quite arbitrary. They're not uniform. But if you look at something like millimeters to a meter, it's 1,000. Meters to a kilometer, that's 1,000. Grams to a kilogram, 1,000 conversion. Kilograms to a ton, 1,000. So again, this is the nice thing about the metric system, is it's usually everything is related to some power of 10, 10 to the n, where n could be a positive integer, 1, 2, 3, 4, 5, or a -1, -1, -2, -3, -4, etc. And that tells you how many places to move a decimal point upon the conversion. Now, let's talk about how the metric system was originally defined. And this was really the brilliant thing that these French scientists did, is they realized we need to make something that is universal, is probably the wrong word, but universal to Earth. And we'll talk a little bit in a second how it wasn't truly universal and what scientists have done since then. But the French scientists knew that we need to make something that was the same all over the globe, right? Anywhere on Earth, this would have the same definition, okay? So they took the globe and they said, okay, well, this one point on the North Pole, right? That distance to the equator is going to be pretty much the same anywhere you are on Earth, right? No matter what your longitude is, that distance between the complete North Pole and the equator is some distance x. We are going to call the meter x divided by 10 million. That's how a meter was first defined. A kilogram was equal to the mass of a cube of water measuring 0.1 meters on each side. So if you take this cube of water, this cube, sorry, that's 0.1 meter by 0.1 meters by 0.1 meters, and fill it up with water, right? The mass of that is going to be 1 kilogram. And so it doesn't matter if you use water, right? Ocean water perhaps, or it really should be deionized or distilled water. But if that's deionized or distilled water in France versus in the United States versus in China versus Australia, that is worldwide going to give you the same definition of what a kilogram is. A liter was set equal to the volume of this cube when it was at a temperature of 4 degrees Celsius. So this cube of water was both for making this fundamental unit of kilogram and defining this fundamental unit of liter, while this was for the fundamental unit of meter. So this is a much better way to do things, because now anywhere on Earth, you could make these measurements and define your unit. You can contrast this with how something like the foot was invented. And the story goes that some king in England knew he needed a measurement system, and so he decided the first 10 men who walked into church this Sunday, we are going to measure their feet, but not both of their feet, just their left feet. We're going to measure this, and we're going to measure that for all 10 of these men. And we're going to average this measurement. And so these 10 men who randomly walked through church on a Sunday had their feet measured. They added all those measurements up, divided by 10, and that was their unit of a foot. And that's how we wound up with the unit of a foot, which is completely arbitrary to the 10 people who happened to walk through church on that Sunday. It's going to be different if you take this measurement of the first 10 men and their left feet who walked through a church near you, right? So the French system is really, really better. The metric system, as it's now known, is better because it's something that's true across the Earth. Now, as we look outward from the Earth, we realize that, well, these might not be the same measurements, right? There's only one Earth where this distance from North Pole to equator is going to be, right, equated to a meter. And so we need something that truly is universal so that a planet in a solar system and a galaxy that is not the Milky Way could make this same type of measurement. So scientists actually last year have been updating some of these, specifically like the kilogram, to be dependent on the speed of light. And so the kilogram is actually no longer attached to this mass of water, which actually had since been updated to the mass of a metal rod. But now we have it attached to the speed of light amongst other fundamental universal constants, right? The speed of light you measure here on Earth should be the same as the speed of light you measure in a different galaxy. So something that's truly more universal. So scientists are still taking steps to sort of update this metric system. While far, far better than the English system, right? We can always do things to make it a little bit more universal. So this is the metric system. Now we're going to move from the history of it to really some of the things we have to commit to memory about the definitions, particularly in terms of these prefixes we talked about. And this is the beauty of the metric system, that by adding any of these prefixes in here that have these abbreviated symbols here, we can communicate to other scientists the relative size of our measurement. So there's a base unit, right, which would live right in between deci and kilo. And while there are more abbreviations than I'm showing here, these are the most common, and these are really the ones that you want to commit to memory most as a scientist. And so the base unit would live right in between here, kilo and deci, right? So whether it's the base unit is meter, whether it is gram, whether it is liter, whether it is second, that's situated here. And now these units of abbreviation and this chart overall is used in the following manner. One of these prefixes, okay, one prefix equals 10 to the n of the base unit. Okay, so let's look at this in action. Let's look at kilogram, perhaps, or kilo, right? 1 kg, where k is the abbreviation, kilo, and the symbol is lowercase k. One of those kilograms is equal to, what is the unit here? 10 to the third. 10 to the third of the base unit grams. And so that's how I use this table. In the same way, if I wanted to look at tera, capital T, you would say 1 teragram, or maybe we can do meters this time, 1 terameter is 10 to the 12 meters. Same will be true down here. You could say 1 of the prefix unit, nanosecond, is 10 to the negative 9 seconds. Okay, and so that's the way this chart is written. Now, some of you probably already have some of these committed to memory. For instance, you might know a millimeter and its relation to a meter. According to this table, we would write 1 millimeter is 10 to the negative 3 meters. Some of you, though, might memorize the reverse of this, right? This is exactly equivalent to the following expression that I could also write. (10 to the third millimeters is 1 meter. And so maybe this is something you have memorized already. Maybe you already know 1,000 millimeters in a meter, right? Or 1,000 milligrams in a gram, 10 to the third millimeters in 1 meter, right? Each of these is saying the exact same thing, right? All I'm outlining here is the way that this chart is written is in terms of the first way to express it. If you want to express it the reverse way, right, where you want the 1 to be with the base unit, like I'm doing here, then you better switch the sign of this exponent. So if you want the 1 to be with the base unit, well, it's not 10 to the negative 3 millimeters, it's 10 to the positive 3. This chart, though, is showing you, as written, one of the prefixes in that many of the base unit. So you need to commit these to memory because you'll often see, gigabytes or terabytes, right? Petaflops of data, right? And you want to know immediately that, a terabyte is 10 to the 12 bytes, that a centigram is, 10 to the negative 2 grams, right? That a picogram is 10 to the negative 12. And these are common things used throughout the sciences. Let's look at these a little bit more in terms of the abbreviations. The names of the metric units are abbreviated with the letter corresponding to the prefix and the base unit. So we've been using these before, but just to spell it out, a kilometer, right? Although these are uppercase here, a lot of times that will only be if it's starting the sentence with that word. And a lot of times you'll see them written as lower cases. But in terms of the prefixes, this K is always lowercase. This M is always lowercase. This N is always lowercase. Micro is actually a Greek letter mu. That's the only one that's not, the letters that we're familiar with. This is the only one that's going to be a Greek prefix. So do keep in mind this one, right? So a lot of these are lowercase. I'm going to put a box around the only ones that are uppercase. They are the largest of these prefixes, right? So going bottom to top, these units are getting bigger, right? Exagram is 10 to the 18 grams versus megagram, which is 10 to the 6, versus nanogram, which is 10 to the negative 9, a really tiny number of grams. So bottom to top is getting larger. So maybe we can take, 30 seconds or so and think about what the name and symbol for the prefix is here. So maybe you can do all of these in grams if you wanted, but concentrate not so much on the prefix, the unit grams or the letter G, but more on what is the prefix that I'm referring to with this size of a number. Okay, so maybe take 30 seconds and try to jot these down. All right, time's up. Let's take a look at this. So we can go back, you might not have memorized these so quickly, right? But 10 to the 6, this is a million, right? 10 to the 6 is a 1 followed by 6 zeros. That's a million. So I always have the mnemonic here that a million is a big number, M for million. That's capital M, okay? So this is mega. And sort of mega millions sounds like something that should go together. So 10 to the 6, a million, that's a capital M, and that stands for mega. 10 to the negative 12, that's pico, and that's a lowercase p. 10 to the third, that's one we're maybe more familiar with, lowercase k, and that is kilo. Just to keep writing these in the same sort of format here. Pico, lowercase p, kilo, lowercase k, mega, uppercase M. 10 to the negative 9. 9 is like nano. That one's easy to remember. And it's negative 9. There's 2 n's in nano. And that is a lowercase n. So again, some of these you might be familiar with, but others you may not be familiar with, particularly atto. When I was in graduate school, I used a lot of nanosecond lasers and femtosecond lasers. And people these days are using even shorter time frame lasers like attosecond spectroscopy. So with that, we've sort of finished up this first lecture where we talked about the abbreviations and the history of the metric system. In the next lecture, we're going to talk a lot about dimensional analysis. right? A lot more quantitatively, how are we going to change from milligrams to kilograms? How are we going to convert from centimeters to inches if we have to go between metric system and the English system? So that'll do it for this video. See you next time.